Welcome, ladies and gentlemen, to this webinar. This webinar is a part of series of webinars and workshops that Rocscience offer for continuous learning. The webinar is entitled NovoTech Software, using NovoTech Software to estimate bearing capacity. Rocscience is a world leader in developing two-dimensional and three-dimensional software for civil, mining, and geotechnical engineers. For over 20 years, we've built geotechnical tools used by more than 8,000 users around the world. We have over 70 employees at our head office in Toronto, more than half of which hold advanced degrees in engineering. Rocscience acquired NovoTech Software, which is a software company based in Vancouver, Canada, last October, and accordingly, the software programs of NovoTech became part of the family of Rocscience software programs. Today, we're going to present two software programs from NovoTech that are related to bearing capacity calculations. My name is Ahmed Mufty. I'm a PhD holder in geotechnical engineering and professional engineering license in Ontario. I'm a geomechanics specialist in Rocscience. My colleague Alireza Afkhami will be participating in presenting the software. He's a holder of a master's degree and a professional engineering license as well. He's a senior manager for web applications in Rocscience. We will start with an overview of methods for bearing capacity computations. The bearing capacity of shallow foundations may be methods for bearing capacity calculations of shallow foundation may be divided into two types. The types are either empirical or theoretical. The empirical methods, whether they are SPT-based methods or other methods, are usually dependent on experimental or empirical nature. And the theoretical methods are based on the general or the shear failure under the foundation. The SPT methods are categorized here separately from other methods of empirical type because we want to show the methods that are included in NovoSPT, which is the software of NovoTech. The four methods that are adopted are Berland and Burbage, Parry, 1977, Mullerhoff, and Peck et al., which is very famous and popular method. And there are many other methods which are not included, they are of less popularity. The theoretical methods usually are starting from Terzaghi, original bearing capacity method, then the Mullerhoff general method, then the Hansen, mostly acceptable as the general bearing capacity formula in practice, Vesic also, and other methods. The software for bearing capacity calculation based on theoretical method is called PEYSANJ, and it adopts Terzaghi and Hansen method. The other methods may include field tests like PLT, plate bearing test, plate loading test, some model footing tests, correlations with cone penetration test results, correlation with California bearing ratio, or correlation with other tests like pressure meter tests or dilatometer tests. Starting with the SPT methods, the SPT is a standard penetration test, has a drop weight and a drop height that are providing energy to push a sampler into the soil. The sampler will penetrate around 45 centimeters in its maximum. The first 15 centimeters is ignored. The second and the third 15 centimeters, summing as 30 centimeters. The blow count for these 30 centimeters is recorded as the SPT blow count. This SPT blow count should be corrected for different situations, for hammer efficiency, for borehole diameter, for sampler type, and for road length. to standardize it to a 60% efficiency. And this blow count is called N60. It's used in many correlations. The N60, some correlations required it to be corrected for overburden, effective overburden pressure of 100 kPa, which makes it standardized for overburden pressure. One of the methods for calculating the correction factor for N60 to N160 is from Peck et al.'s relationship, which is very famous and known for most of you. And also, there are many methods depending on the local situations and local experience, soil types, other things, even the codes. For example, British standards have different CN, other codes have different CN, something like that. The correction factors for the hammer efficiency depends on the local experience and the type of the hammer. The correction factors are also used, as I said, for diameter, because there may be different diameters for the hole. We have also correction factors for road length, because when you go deeper, your road length will affect the energy transferred to the bottom. And also, the last one is the correction for sampler type. Another correction occasionally applied in some cases, that is when you have a silt material under the water table, so it needs a correction. If your N is more than 15, so you need to correct. For gravel or sand, which is very dense, you need to correct, also apply another correction for the blow count. The SPT methods adopted in this software, which is NovoSPT, are the Berlin and Burbage, a popular method. Usually we base the allowable bearing pressure to base it on allowable settlement. In empirical methods, the ultimate bearing capacity is usually very high compared to the allowable bearing pressure controlled by the allowable settlement. That's why the empirical methods mostly adopt some allowable settlement relation. And the mostly used allowable settlements to 25 millimeters, but you can change that to a different allowable settlement and get the corresponding allowable bearing pressure. The second method is PEYSANJ 1977. Again, it's for 25 millimeters allowable settlement, and it correlates the allowable pressure with the SPT N60 directly. If you have different, but this is controlled by that the depth of the footing is less than the width of the footing, and the value of N60 used here in the equation and in all the methods based on SPT, they should be average within an influence zone, varies from a method to another, to be averaged at that zone and used in the equation. The third method, which is also very popular, is the Mullerhoff method, which has some factors correcting for depth. And the influence zone here is different from 0.5B to 2B below the foundation level. The fourth method is Peck, Hansen, and Thornburg method, which also correlates the N160 with the allowable settlement of 25 millimeters, and it has a correction factor for the water table, groundwater table location. The theoretical methods are different. We don't base in theoretical methods the ultimate bearing capacity or allowable bearing capacity based on settlement. We derive or we use formulas for defining the bearing capacity from the assumed shear failure of the soil pattern, the shear failure pattern of the soil. So we have general shear failure, we have local shear failure, and we have punching shear failure. The behavior of the soil within these three types are different. So you need to be sure from the beginning, or at least close to what will happen in your footing, whether you are within the general shear failure zone or local shear failure zone or punching shear failure zone. If you are in general shear failure zone, you can use your shear strength parameters as they are obtained from the tests, whether from plane strain test or triaxial tests or direct shear test. But if you are in local shear failure or punching shear failure zones, you need to decrease these parameters by 2/3 at least. Terzaki's method is the basis of all next methods in the literature. They all have the three terms for the bearing capacity equation, which include three factors. They are called bearing capacity factors: N sub C, N sub Q, and sub gamma. And the methods differ by defining how they define these parameters, because the assumption of the failure pattern or the shear failure happening is different from a method to another. These factors are corresponding or used with a corresponding term in the bearing capacity equation. For example, N sub C is used with cohesion, N sub Q is used with the effective overburden pressure at the base of the footing, and N sub gamma is used with the unit weight beneath the footing, effective unit weight beneath the footing. These factors are all dependent on the angle of internal friction used for defining the soil material. And the bearing capacity equation is derived for strip footings, long strip footings. So if you have round footing or square footing, you need to apply shape factors to the first and the third term in Terzaki's equation. Terzaki's equation neglects the shear resistance at the soil above the base of the footing. It assumes a rigid footing with rough surface in contact with the soil, and the depth of the footing should be less than or equal to the width of the footing. This is also a general approach to define a shallow foundation. The second method is Mullerhoff method. This is not in NovoTech PEYSANJ software, but we will go very fast through it. It's the difference here that Mullerhoff included depth factors to add that shear strength resistance of the topsoil, and added inclination factors, replacing the shape factors if you have an inclined load. So if you have a vertical and horizontal load applied to the footing, you need to apply inclination factors. The theoretical methods also take into consideration the eccentric loading conditions, where a moment will push the applied load away from the center of gravity of the footing with an eccentricity. That eccentricity may be less than B/6 or above B/6, which is the kern of the section. And if it is below B/6, you will have a maximum bearing pressure on one side and minimum bearing pressure on the other side, making a trapezoidal distribution of bearing pressure under the footing. While if you have a larger eccentricity, part of the footing may have no pressure at all, and the rest will be under triangular bearing pressure, or applying a triangular bearing pressure with a maximum bearing pressure on one side. The maximum bearing pressure here should be checked with the ultimate bearing capacity from the equation. Of course, Q minimum in this case is 0. Mullerhoff applied another way to deal with eccentric loading. He assumed an effective area for the footing, with the center of that effective area as being the point of load application. So that's why a new width and a new length, which are effective length L prime, effective width B prime, are used in some of the terms of the bearing capacity equation. Hansen method is a more general method than all the other methods, and it has, in addition to the depth factor and inclination factor, he introduced ground slope factors and base inclination factors. So the general bearing capacity equation became too long with many terms. You need to go over each term, how it is applied and how it is calculated. And he also separated another equation distinguished from the above for the phi equals 0 conditions, which is a completely total stress analysis for clay soils. So here are the shape factors of Hansen method, the depth factors. The depth factors may depend on the depth over B ratio, which is very important. And you can see here in the shape factors, we are using B prime and L prime instead of B and L. So if you have no inclination, no eccentricity for the load, you can use B and L here instead of B prime, L prime. Inclination factors of Hansen, ground slope factors for Hansen, and lastly, the base factors. The angle of the base, eta, and the angle of the ground slope, beta and eta should be less than or equal 90, summation of beta and eta. And these are the positive directions, how you take eta and beta from the horizontal. The last correction is for water table. The water table may be above the ground the base of the footing, or maybe below the base of the footing, and this affects our calculation for the effective overburden pressure if it is above the water, if it is above the base of the footing. So you need to calculate the summation of effective pressure, overburden pressure from D1 and D2, and if the water table is below the ground, the base of the footing, then small d, if is above the width of the is more than the width of the footing, then you don't need to correct anything. If it is between B and 0, the base of the footing, then you need to correct the effective buoyant unit weight at the third term of Terzaki. With this slide, I'm ending my part. I'll pass the presentation to my colleague, Alireza. Alireza, please, you can share your screen. Thank you.
Hello, everyone, and thanks very much, Dr. Mufty, for good presentation and an overview of the bearing capacity. Yeah, I appreciate it. As Dr. Mufty mentioned, with NovoTech, we have a number of computer programs for geotechnical engineering. Some of you may be familiar with these programs, programs for CPT, for liquefaction, for bearing capacity, and so on. Today, we are going to talk about two of these programs. One of them is NovoSVT, and the other one is PEYSANJ. NovoSVT is mainly based on SVT correlations and bearing capacity SVTs, and PEYSANJ is about the traditional Terzaki based, essentially, bearing capacity. Now, with the SVT, I'm sure you agree that SVT is the most common geotechnical field test. A lot of us have used SVT before, and typically what we do, we collect data for 12 inches of penetration, and then we correct the field SVT for various type of corrections, and Dr. Mufti went over those corrections, and then we can use, once we have the corrected SVT numbers, we can use them for correlation to different soil properties, and also, of course, use them for bearing capacity estimations. With SVT, as mentioned before, we typically collect this data for 12 inches of penetration. In some cases, we do this collection of SVT data for multiple segments of 6 inches of penetration, let's say 4 6-inch segments, and then depending on whether the SVT is done on drill cuttings or other types of errors in the data and drilling, we may choose the middle 2 6-inch of penetration as a representative N value. But SVT is not the only penetrometer test that we use. In addition to SVT, in North America, we use Becker penetration test and dynamic cone penetration tests, which are very similar to SVT concept, but then their number are different. And what you can do, you can use typical correlations between, for example, a Becker penetrometer test and convert those to N60 for further analyses, either correlations or liquefaction analyses or bearing capacity. With NovoSVT, we assume that you already have the field N value, and you can enter these numbers either manually or import from text or CSV or what, and then from that point on, you can use those for further correlations. The corrections that we apply on N value, as Dr. Mufty mentioned, are hammer energy, rod length, sampler, borehole size. You see a lot of these data and also the equations that mentioned before. You can see them in NovoSVT help file for documentation. With regards to the additional corrections, we have like water level corrections, which is mainly used for bearing capacity calculation, and also overburden and stress correction, C sub N. We're using C sub N, we can calculate our N160, and N160 is used in some of the bearing capacity calculations, in some of the correlations with SVT. For example, I've seen those in shear wave velocity correlations. And as you know, C sub N for overburden and stress correction depends mainly on depths or sigma prime V, the overburden and stress. So with NovoSVT, we can correlate data to various soil properties. Here you see a list of these soil properties. In addition to these, we have a couple of other modules in NovoSVT for other types of calculation that we don't focus on those today, but we'll take a look at how NovoSVT can help us make our life essentially much easier, especially if you're a type of engineer or consulting firm that use SVT a lot in your projects. Almost everyone has come up with some sort of spreadsheet to process the SVT data. One problem with that is that you will be limited to a number of correlation for each soil properties. For example, if you want to correlate to internal friction angle, then you have 2 or 3 correlations only based on the textbooks. But what we have done in NovoSVT, we've added more than 325 SVT correlations to the database of NovoSVT, And we've done this by going through more than 70 different textbooks and published articles, and essentially detailing each of these for the type of soil that each correlation is valid for. And that's another important point when you compare NovoSVT with like spreadsheets or hand calculations. Each correlation is developed for a certain type of soil, and we have all of these in NovoSVT. Now, switching to bearing capacity analyses, as Dr. Mufty mentioned, we have 4 main methods of bearing capacity calculation based on SPT, and these are generally developed for 1 inch of settlement. So this is the allowable bearing capacity for 1 inch settlement only, and these are, I should say that these are derived for footings sitting on sand generally. In addition to that, what we did, we also brought in the Terzaghi general bearing capacity equation. And because assuming that we are looking at sand, then there is no cohesion for material, then the main parameters to estimate will be NQ and N gamma, and we can estimate those from friction angle. So as long as you have a correlation for, or a correlated value for friction angle, then you can estimate NQ and gamma, and there you go. You can use Terzaghi equation to come up with the bearing capacity. Now at this point, I'm going to switch to NovoSVT and give you a general idea of how you can use the program. So this is the main page of NovoSVT. As you can see on the top left portion, in this table, you can enter the soil layers with their thickness and unit weight and soil type. And soil type is just a guide for the program to go through the correlations, and if you want to filter invalid correlations, then depending on the soil type, we can do that. On the right side, you will enter the SVTs, and these are the field SVT blow counts. These are just field N values that your engineer has collected on site along depths of the borehole, and the program will do the calculation, the corrections, and come up with N60, CN, and N160. Now, in this section here, the SVT corrections, you can apply corrections, and you can ignore corrections. You can remove this checkbox if you somehow did your own correction, let's say in a spreadsheet or something, and you're actually importing N60 values into the program. In that case, all the corrections will be taken as 1 in the program, so that your N60 will be the same as your N value. But assuming that we are going to do corrections using NovoSVT, we keep that on, and you can choose the borehole diameter and sampling method, and for overburden correction, you can choose from different methods here. And these are for obviously N160 and C sub N factor. If you have groundwater level, you can select these and enter groundwater depth, and you can also choose to filter the SPT data, SPT correlations for soil type. So what I'm going to do, I'm loading an example data here. So this is an example data. You see we have 4 different soil layers of different types. D50 is used in a couple of correlations, so we keep it here in this table. But when you choose the the type of material here, it will actually suggest to you an average D50, but you can change it if you want. So here we have the SVT blow counts. These are the field values again, and on the right side you see that the N60 is calculated, and N160 is also calculated and plotted here for you. In all of our NovoTech programs, when you see a chart, you can easily click on the chart, and it will give you the detailed numbers. You can print it, you can save it as text file or JPEG file, you know, something that you want to put or include in your geotechnical report. You can easily do that. So now we start the analysis here. So I'm going ahead and add groundwater level and start the analysis. And here you are. So these, so here, as you see, I've selected shear wave velocity, but let's say we are looking for friction angle. So here is friction angle at what depth? So we are looking for friction angle at 2.74 meter depth. And as you see, and 2.7 meter, just going back here, 2.7 meter, we are still in clay. So let's go into sand. So we go to, let's say 3.66. Okay. So now we have different values for friction angle, and these are based on different correlations or different methods used in the program. For each of the correlations, what you can see here, you can see the comments, and you can see the reference number, and this is the book reference or the article reference. If you go to the documentation, you will see what is number 45, which book it is, and then it also gives you the variable that used in the correlation. For example, in this case, this is relative density that is mainly used, but relative density itself is correlated from SVT. But for the other ones, you see N60 and 160 is generally used. And for each of these correlations here, you see the actual equation. This was added in our most recent version of the program in 2020. So now we have a couple other features with NovoSVT that I don't have time to go and get to those, but just letting you know that we have the correlation with depths, and what this does is that it plots the correlated values for that specific soil parameter along the depths. And this is very helpful because if you want to do some sort of modeling for the slope stability, or you're using any other of our programs, Rocscience programs that need input, then you can just look at variation of modulus of elasticity, shear wave velocity, friction angle, underhand shear strength with depth, and just use that to as an input to other Rocscience programs. So I just jumped to the bearing capacity page here. So again, I'm not getting into the details of the theory because we already talked about them. But generally, what you can do on this page, you'll specify this factor of safety, and this is only for Terzaghi method because that is the like shear failure based method, which uses factor of safety to come up with allowable bearing capacity. But the other methods are based on 25 millimeter of settlement, but we still included Terzaghi. So here you can specify the footing depths. Because I had already selected 3.66, it's here by default, but I can change it to, you know, whatever number I want. And then the footing embedment, which is typically about 1.5 feet, you know, this is just the embedment, you know, between underside of the footing to the slab, to the slab on grade, the floor slab. And here you can say I want to look at the bearing capacity for footing width from 1 to 3 meters, or you can change it. So as soon as I click on calculate button, then here you see the like different curves for bearing capacity. And if you see that these numbers are in some cases significantly different, welcome to geotechnical engineering. I'm sure you're not surprised. For any aspects of geotechnical engineering, we always have, you know, from traditional equations and methods, we always have different methods and different numbers. It's definitely up to our engineering judgment to come up with the most suitable method or the average or whatever our engineering judgment is. For PEYSANJ method, if you see that we don't have any number under 2 meter width, is because this method is valid only for d over b of, or b over d of greater than 1. So if I change this, then you will see that you will get all these numbers here. So that gives you a general idea of NovoSVT. It's a very useful program. I recommend that you download the program. We have a trial version, 14-day trial version. At the end, I'll explain how you can get your copy of NovoSVT, but it will make your life much easier if you use SVT in your day-to-day analysis. We also have a NovoLeak program that does liquefaction analysis based on different methods using SVT data. So just putting it out there. I'm coming back to the presentation here, and I'm going to switch to our other program, PEYSANJ. So PEYSANJ, as mentioned before, we want to talk about the bearing capacity features in PEYSANJ. But PEYSANJ is a combination of different modules for bearing capacity, stress analysis, plate loading tests, and pressure meter tests. Today, we are going to only focus on bearing capacity. Now, in general, the shear failure-based bearing capacity increases with footing size. So a larger footing obviously has a larger shear failure bearing capacity, and that's because in the third term of general Terzaghi equation we have B, so that we know. Now on the other side, we know that settlement also increases with footing size. So a larger footing will have generally will have a larger settlement. And now larger settlement doesn't help us much, because in reality we have to limit the settlement to let's say 1 inch, you know, for pad and strip footing. For raft foundations we can go with higher settlements because of the, you know, the whole load distribution of those type of footings. But let's say if we limit the settlement for performance and practicality to like 1 inch, then find the bearing pressure corresponding to that 1 inch, then we will see that we'll have a descending curve like this. So for a larger footing, because settlement is higher, if we lower the settlement to say 1 inch, then our bearing pressure here will be lower, right? So we will have, if you look at the first graph, the left graph and the right graph, you see that shear failure based is increasing and settlement based is decreasing. Now let's bring those two into the same graph here. So I bring the blue graph, the cyan graph, and I add the red graph. So this is what we essentially have. So at each point, for each footing width on this graph, we have two numbers to deal with. You know, one number from intersection with the blue graph, the other one with the red graph. So technically what we should do in order to satisfy both criteria, shear failure and settlement, we have to look at these two numbers and just pick the lower number and say, okay, this is a safe bearing pressure for the footing that I can use in my geotechnical report, because I know that with this shear failure is not going to happen. You know, you've divided your QU by factor of safety, come up with your allowable shear failure, and also you know that the settlement will be less than 1 inch, for example, right? So if you follow the same approach, then you will have this green line here, which is the lower envelope of these two red and blue graph. So that's essentially what we do with PEYSANJ. So in PEYSANJ, we do all of these calculations for you using traditional calculation methods for settlement, and also hansen method for bearing capacity. Here I need to get into the zone of influence thing, because zone of influence is when you deal with multi-layer stratigraphy, you have to choose the depths of the influence. So because what we do in PEYSANJ, we calculate the average soil properties below the footing. So we have to decide whether we are looking at 1B, 1.5B, 2B, and you know that in a lot of geotechnical engineering textbooks, they talk about the stress distribution below the footing as a criteria for zone of influence. So what we do in PEYSANJ, we allow user to set the percentage of the applied load. So let's say if you have the load P for bearing pressure, then you ask PEYSANJ that my zone of influence is where the stress increase in the soil reaches to or becomes 20% of the load at the top, or 10%. It's up to you. You can define it in PEYSANJ. So once you have this H, then the rest of it is simple. So we start calculating the average mechanical properties, and once we have that within that H, then we start doing the shear failure calculations using Hansen method, which is more comprehensive than general Terzaghi method. We get QU, we divide it by factor of safety, we obtain QA, and at that point we go to settlement and we check settlement. So with settlement, what it works is that we get the QA and calculate the settlement for QA. If it was within the allowable settlement, let's say we choose 1 inch. So if settlement is less than 1 inch, then that's good. We go ahead with that QA from shear failure calculation as my allowable bearing capacity for that footing size. But if the settlement for this QA is more than 1 inch, then we come back and start from zero, increase the load, increase the stress or bearing pressure below the footing, and calculate settlement. And remember, for each different Q or bearing pressure, you may have different zone of influence, and so your settlement is a function of all of these, and all these equations and calculations are done in a matter of seconds in PEYSANJ. So the final number that you get with PEYSANJ, you know that both of these criteria are satisfied. So I'm going to switch to PEYSANJ for a minute here. Okay, you should be able to see my screen here. Okay, so I'm going ahead and loading an example project. Okay, so here's an example project. We have 3 soil layers here at the top, as you see. We define these layers with their density, cohesion, friction angle, modulus of elasticity, void ratio, and if, like, for example, for clay layer, you can define C sub C, C sub S for consolidation calculations. And now I come to this section for foundation information. You enter the footing L over B, and remember, we just get L over B from user because here the graphs are calculating, for different footing sizes. So we just need L over B to calculate L. B is essentially here. And DF, embedment depths, excavation depths, which is D in the settlement and in bearing capacity calculations. And if you want to apply loads, because Hansen method accepts horizontal load, vertical load, and moments, you define the average unit weight above the footing, ground water level, and factor of safety for shear failure calculations. These are all here. Also, we talked about the allowable settlement, so you can define it here. If you have a more sensitive machinery or equipment sitting on your footing, and your allowable settlement is 1/2 inch, for example, you can change it to 1/2 inch. And what else we have here is the reloading factor, and these are all explained in PEYSANJ documentation, but just reloading factor. So reloading factor is when you excavate, if you follow a plate loading test, when you unload, like if you go to 10, let's say kPa, and you come back to 0 unload for the first cycle, and when you come back up, you see that the slope of that reloading is multiple times the slope of the initial loading cycle. The reason is the material has been pre-consolidated, essentially. So you can see the effect of that here. If you don't believe in this and you don't want to bring the reloading factor, just put 1 here, and everything will be using just 1 modulus of elasticity in your settlement calculations. So now, if I press calculate, I will have this graph. You are familiar with this graph. We already talked about how we deal with coming up with 2 different curves. One curve is for shear failure, the other curve is for settlement, and then we just choose the lower envelope of these 2 curves as the allowable bearing capacity. Now, in this graph here, you see the settlement for each footing width. For example, here at 1.2 meter size of the footing, you see that, or let's look at the first one, actually, the 0.9. So at 0.9 meters, you see that with our settlement, so the settlement bearing capacity is higher than the shear failure bearing capacity, and that's why you see that total settlement is actually less than the allowable settlement specified. But these two curves intersect at about 1.2 meter footing size. So you see that from this point on, the settlement is now governing the bearing capacity, and you see the settlement is sitting at 2.54 centimeter, which is 1 inch, and this is summation of our consolidation settlement plus the elastic settlement. So both of these are calculated, and these are added together. Now we have the total settlement here. You can change data and see how it affects. For example, if I change L over B to 5, then you see that you will get a completely different graph. The reason is when I increase L over B, the footing size is bigger, so the settlement is bigger, right? So you see that what happens is that settlement becomes governing all the calculation, and shear failure calculations are essentially higher than settlement. Now, We can also change the type of the footing. So here we were looking at a strip or pad footings. We can look at the raft footing, let's say rectangular footing, and I change the footing size like 8 by 12 meters. Right, so I'm changing these, and also the allowable settlement, for raft footings based on the reference books, we can choose different or a larger allowable settlement, let's say 3 inches. Now, if I click calculate, then here, see that I have a graph here that shows me the total settlement versus a stress. Like for 60 kPa, I have here a total settlement of close to 12 centimeter. You can use these to come up with your, based on your criteria of 7.5. We enter 7.5 here, and the program finds the settlement based on, the Q allowable based on the 7.5 centimeter. In this case, it says 40 kPa, but you can just look at the graph, and for any settlement criteria, you can come up with the corresponding stress. The reason that we present this data this way for raft foundation is that for raft footings, generally speaking, your shear failure criteria gives you a much higher bearing capacity. In this case, for example, the shear failure base Q allowable here is more than 100 kPa. And you see that the settlement based criteria is much lower. If you want to see the details, here you click on show details, and this was actually for the, go back to the strip footing. Yeah, so here, if you want to see the details, we have all the details for each footing size. You can see the average soil parameters calculated. The bearing capacity parameters also calculated here, and also the rest of the parameters. We also have a relatively fancy calculation details here provided in a PDF if you like. So that's generally what we have with PEYSANJ. Our time is almost up, so I'm going back to the presentation, just letting you know that you can easily download our programs just by going to our website, go to downloads menu, and click on download trial versions, and you'll see a simple form. Once you enter the form and submit it, you will get a trial license key in just 5 minutes. Very easy.
Thank you, Alireza, for your presentation. I would suggest, I would urge the attendees to write their questions in the questions area or on your webinar window, right side. And there's one question I would like you to answer. The question is from Mr. Gerald Innocent Autumn. He's asking if it is observed N60 is generally used in the SPT calculation using NovoSPT software. Is it possible to also use, say, N55 or N70 depending on client's requests or project requirements?
So in NovoSPT, what we do, we use the published correlations, and these published correlations are generally based on N60. I remember some of the correlations based on N70 and N55, and what we do for those correlations, we just adjust the N values to obtain N55 and N70 based on Hammer energy adjustment. But for the other correlations, if they use N60 or N160, we have to use those values. I think if we want to make sure that the numbers we get are valid. But if you maybe send me an email like with a little bit more information, more details about what type of equation or correlation you want to use, just send me please an email, info@novotechsoftware.com, and I'll be happy to help. Any other question you can also email me.
There's another question. Please, Mr. Gerald, if you like more communication with Alireza, send an email to him. Can you write your email, Alireza, or it's you can write it in your presentation somewhere if you can, or he can contact Rocscience marketing team, and they will or tech support, they will transfer the question to you.
I sent it in the chat.
A special message will be fine. Yeah. There's another question saying, thank you very much for your beautiful presentation. Does NovoSPT have the ability to calculate in SPT drillings made on rafts in marine and lake environments?
So
I will adjust the question. Does marine and lake environments change anything in NovoSPT to calculate your factors or SPT bearing capacity equations or anything like that?
So the only thing that I can think of is that if you have like in that condition, like you will have standing water essentially above the ground surface. So seabed becomes the ground surface in our modeling, and you will have the groundwater level above the ground. And I think we don't have this because we have to come up with a solution with a way to adjust the sigma prime V. Because all assumption is that your groundwater level is below the ground surface. But we can look into that. What I suggest is you send an email to me, and then we work together just to make sure that we can cover all aspects of these type of calculations. I have to think about also the SPT corrections. You know, is there any criteria for SPT correction when part of the rod length is not supported, like in terms of buckling and energy distribution and all that? Is it going to affect our rod length correction?
And another question. That question was from Gural Özdemir. The next question is from Eddie Montalvan. He says, or she says, I'm not sure. I really like the chart where you presented sheaf area and settlement-based bearing capacity. These charts are similar to the recommended one by some authors using LRFD method. It would be nice if you add LRFD to your software. Is it possible or not? Is it already included in the software?
So
just faster, please, because we are lacking time.
Yeah,
we are almost 1 hour now.
So the short answer is no, but what you can do, you can because like in LRFD or ultimate limit state design,
I believe he should add his own factors before.
Yeah, that's what I'm saying. So you can use
question. Yeah, I'm sorry, Ali. I need to finish this. Albano Ajuda. The question is, how about seismic bearing capacity, etc.?
We don't have this in PEYSANJ.
I'm not sure how that will affect the calculations. You might play with the parameters, shear strength parameters.
Yeah, I've seen some equations for calculations in seismic conditions. If you're talking about those specific equations, we don't have them in PEYSANJ, but you can always apply horizontal load in PEYSANJ calculation. You apply horizontal load for seismic base shear and see how does it affect the calculation.
It's like you will calculate the bearing capacity in a pseudostatic.
Yeah. You can look at it pseudostatic, but if you're talking about some seismic specific calculations, no. And again, if I have Dr. Mufty just a few seconds here. So with LRFT question, you can use the factor of safety as a means to model your LRFT geotechnical resistance factor. For example, if you put factor of safety of 2, mathematically it is equal to a geotechnical resistance factor of 0.5 on the QU calculated by PEYSANJ. So depending on what geotechnical resistance factor you want to use for bearing capacity, you can remodel it with just reverse it, invert it to turn into factor of safety and use it in PEYSANJ.
There's a comment from Eric Cruz. Well, the foundations lying in seabed, the effective bearing capacity of the soil will not change even if the water table is above seabed. Well, I don't think the issue is in the bearing capacity itself. It's in the how you deal with the SPT correction factors. And with this comment, also he has left already. We are ending our presentation today, thanking everybody attended, and wish you a good day ahead. And thanks for everyone. Thanks, Alireza. Thanks, Sayona, for being with us and helping us. So goodbye, everybody. Thank you.
Thanks, everybody.